order logic, it turns out that we'll see there that in the first order logic, not only do you have states that describe the objects and the objects have interrelations, but you may also have functions over objects. And you give an object to a function, it spits out a new object. The moment you have a function, in theory, you have infinite number of objects. Do you understand what I'm saying? This is why the moment those of you who have taken any logic courses, I don't know whether any of you are there, the moment you throw in piano arithmetic, things go out of control, because the successor function, essentially you start with just one. I only have one number, 1 or maybe 0, just object 0, and then I have this simple function called successor function that gives me the next number. Now how many numbers do I have now? Infinite number of numbers. Now proving things in that case winds up requiring, for example, things like mathematical induction. Right? Okay, so in the first order logic you also have functions over objects. It turns out in that case, honestly, if you do, relational can be compiled back to propositional, propositional can be compiled back to atomic, thus keeping this view of higher level versus lower level languages. Okay, and it is reasonable, it's reasonable to understand first how everything works in machine language before you start understanding everything else. That's why we will first understand search in atomic representations, then understand planning in propositional representations, and perhaps go towards relation. Okay, but the advantage of going this way is this actually might have this has the argument that we finally have limited brains. We don't have infinite capacity. More importantly, ants have really limited brains, and they seem to be doing pretty impressive things. Okay, so the question is, how does an organism which actually has limited brain power handle a world which has infinite number of states? I can't say that ants use logic, but higher level languages allow you these compactness characters. So that's one reason why we will understand how to do these inferences with representations that are higher level than atomic representations. That said, we first need to understand everything in atomic before going on. So that's why we'll start with atomic search, atomic multi-agent search, then go to relational single-agent search, propositional single-agent search, and then we also do, at that point we'll actually start doing a slightly different change to our assumptions. We'll stop the determinism assumption, we'll allow uncertainty in. So if you have propositional representations and uncertainty, we will start talking about things like Bayes networks, which are essentially logic with probabilities. Probabilistic logic. Okay? So there was a question.
Yeah, so an example of a function over an object would be like including human behavior in your model for the taxi driver and like iterating that over.
No, actually no. Here I'm just something as simple as successor function in numbers, okay? Or if you are writing, let's say, a knowledge base over people and their sibling relationships, right? Like, Tom, John, and say Tom is the brother of John, etc. Then, for example, if you have father of can be a function. Father can be a function, okay? Or mother can be a function. And if you take an object and give it to mother, it will give the mother object. You can then apply the mother to that function, that object, you get the next mother object. So it's just a way of developing a huge number of, basically you are effectively developing a huge number of objects. Okay. In first order logic, in all these cases, the number of objects are finite. The moment you throw in functions, in effect, you are allowing infinite number of objects. Other questions? Okay. So that's basically the big picture I want you to keep in mind. And for the atomic search, as I said, I was going to look at the depth first, breadth first, and iterative deepening, etc. searches. But before I get there, let me use the rest of today's time to talk about. So I said there is determinism. That means the environment. So the actions of the agent are deterministic. I said it's static. That means there are no other agents. What didn't I say? What is the other piece that I didn't talk about? Observability. It turns out that actually in this very simple model, I can start talking about observability, okay? By saying if I don't know where I am, it means I'm in one of the possible states. So if my entire world that I live in can only, suppose my entire world I can live in has only 18 different possible states. And I come and tell you I don't know which state I am in. It's not the end of the world, it's just one of 18 different states, that's it. You understand what I'm saying? So essentially, the search then has to be not in terms of single states, but in terms of sets of states. Okay, but let me point that out with this vacuum agent example, and then we'll come back. And then most likely, what you will do is you will get through the lectures on blind search by reading the lecture, because I sort of gave a quick, introduction to them. You will see the video, and we'll come back and talk about it once. Okay, but here with the vacuum world, these are the distinctions between atomic, propositional, and relational representations. Okay, so this is the vacuum world they talked about. You could have called it Roomba world. So basically, there are two rooms, and there may be dirt in them or not, and the vacuum can be either the left or right. So in this particular scenario, so this is the way the worlds are to you. Now, of course, you look at this and you say, essentially, I know what's going on. This is left room, this is right room, and this is in, the robot is in right room, is true here. Robot is in left room, is true here, etc. But if you think of these as indivisible state representations, these are 8 pictures, 8 snapshots of the world. Okay, and so in an atomic representation, you just see 8 different states. Okay, and if you were to have a children generated function, whenever the agent does an action, in essence, it generates new pictures, new indivisible states. So for example, if I'm in this state and I do the suck action, then what happens? I get to state 5. There you go. Okay, and similarly, if I'm in this state and I go do the go right action, I will be in state 2. You see what I'm saying? Now, your agent doesn't have to know this. I just write this up in the child generator function. I, the programmer, write this up in the child generator function. So I have 8 different states. Each state is seen as an indivisible snapshot. All actions are state-by-state matrices. That is the 8x8 matrix. And if you do an action in a state S, he'll tell you what state you will get to by putting a 1 there. Think of that way. Actions can be written as a state-by-state matrices. Okay. Now the interesting thing about that is if you write actions as 8x8 matrices, and so if this is S3, and if I do an action, let's say if I put 1 here, that means if I do S3, I'll get to S5. That representation also allows me to actually handle probabilistic and non-deterministic actions. Probabilistic means I'll put numbers which are between 0 and 1 such that they add up to 1 in the row. That will be a stochastic action. Non-deterministic action just puts 1s in all the states that you might get into after you do this action. Right? That's the way of getting stochasticity and non-determinism in this representation. When you do propositional or factored representation, really you only think in terms of these 3 propositions. Dirt in the left room, yes or no. Dirt in the right room, yes or no. Roomba in room, left or right. 3 variables, each can take 2 different values. So there's 2 power 3, 8 different states. So it looks like I went from having to deal with 8 states to dealing with 3 state variables. Because logarithms in the size of the number of indivisible states. That's the compaction I was talking about. And so here the planning representations would be directly talking in terms of these state variables and how when you do an action, how a state variable's value will go from one valuation to another valuation. Here, in this case, I go directly from a state to a different state. Here I describe an action in terms of how it doctors each one of the state variables. Okay, so the representation will change. We'll get to that later. And the relations will, for example, would be things like in robot room, dirty room, etc., which is basically you have predicates and the objects. So that's the kind of distinction. So the same word represented in 3 different ways. Just like you can have the same task, write an assembly language program, a C program, and a Lisp program. Right? And I meant higher and higher in terms of abstraction. Right? And or closure or something. And so basically the Lisps and the closures are on this basically higher level. And so they can be compact. Right? And a higher level language can write like a 3-line program that when you actually expand it in the machine language might be 8 pages. That's compact. Right? So actually we'll stop here. One other point I did make is if in fact you are trying to go from, if you don't know where you are, in this kind of scenario, I might say the robot is in state 1 and it needs to go to state 8 or state 7. It turns out it doesn't really matter. Suppose all you want is the room to be clean, then the goal test will say yes to either of these states, because in both these cases the rooms are clean. Okay. Now the interesting question is, if I did not know in the beginning where the robot is, and I still want to clean the rooms, can I do that? Yes. Suck, move until you're done. Right? So it turns out that the picture is this. So normal vacuum world has this state graph underlying it. You should look at this carefully. These are the states and the edges are named by the actions. And so if you are in this state, you do the write action, you get to this state. If you are in this state, you do the suck action, you get to this state, and so on. So the size of the graph is the number of states. Now if I don't know which state I am in the beginning, I could be in any one of the original 8 states. You understand what I'm saying? Not saying I don't know where I am, is saying I'm in possibly every possible state. Now, lucky for you, there are only 8 possible states. So it's like you call, Mom, I don't know where my wallet is. Thankfully, there are only 3 rooms, so it has to be in one of those 3 rooms. Right? And you'll wind up searching those 3 rooms. So here there are 8 states. So the initial state is this belief state, telling you that the robot is in one of these 8 states. The final state is still the goal state, which is either this or this. Now the interesting thing is, look at this graph when you go back. When you are in this belief state and you do right, what happens? You will be in this state. Irrespective of, even though you didn't know which of the states you are in, once you do right, you will surely be in the right route. So that means that uncertainty of the state reduced from 8 states to 4 states. One of the most interesting things, there are 2 interesting things that are going on here. One is, previously the number of states was 8. The number of subsets of 8 things is how much? If you have 8 things and you write all possible subsets of these things, how many subsets are there? 2 power 8. Do you understand what I'm saying? So now the real thing is that the number of propositions is 3. So the number of states is 2 power 3. So the number of sets of states is 2 power 3.
I see. Right.
Now 2 power 3 should make you wake up in cold sweat if you are a computer science major. 2 power 3 you should have a heart attack and die because it's too late. But basically not having vision is when the robot won't know which room it is in. If you ever wondered what is my friend who is sort of visually challenged must be going through, this is what they're going through. They are searching in a much larger space than you are searching. It's just exponentially larger space. Secondly, when you do actions, previously actions were only changing the state of the environment. Here, the actions change your belief state. So just by going right, you reduce the uncertainty about where you are. So if you ever wake up in somebody's room, I don't know why, and you want to go to the bathroom, and you don't want to wake up the person next to you, what do people normally do? They get up, if it's dark, they get up, they find the wall and follow the wall. Why did they find the wall? They wanted to go to the bathroom. Why go to the wall? It doesn't make any sense to go to the wall, right? It only makes sense because you are reducing your uncertainty. You are first localizing yourself by going to the wall, and then from there you are going to the place where you wanted to go. All of that is shown in this little graph. Because if you look at what each of these actions are doing, they are actually reducing both the uncertainty in your state and also getting you towards the goal. Okay, so now it turns out that the search algorithms that we look at, that you will be hearing about in the lecture that you will hear, could be given as input either this graph or this graph. It could care less. It would work on either of them. All that changed is for the search algorithm, if you give this graph, you give the children generator function that's inherent here. If you give that graph, you have to give the children generator function that's inherent. That's it. It'll be just a larger graph. We'll stop here. Sorry we went 5 minutes late. But I will send you the exact lecture you have to watch, and then we'll come back and